et à toutes. Mon nom est François Proulx de l'Université Laval. Il y a Manuel Rodriguez qui est aussi avec nous, qui est professeur titulaire à l'École supérieure en aménagement et développement régional et aussi titulaire de la chaire de recherche en eau potable. Nous vous remercions d'avoir répondu nombreux et nombreuses à cette invitation de la chaire et aussi du Centre de recherche en aménagement du territoire, le CRAD, pour cette 6e et dernière visioconférence de la programmation de l'automne 2021. J'en profite aussi, parce que je ne l'ai pas fait dans le passé, pour remercier Claudia Larochelle qui nous a été d'un appui extraordinaire durant toute cette saison de conférence. Donc, avant de commencer, on répète toujours les règles, même je pense qu'elles sont connues de tous et de toutes. On vous demande de garder vos micros fermés et vos caméras fermées pendant la durée de la conférence. Celle-ci devrait durer entre 20 et 30 minutes. Vous pouvez à tout moment utiliser la fonction clavardage de Zoom pour poser une question à la conférencière. Donc, si vous voulez la poser vous-même, vous avez juste à le demander et je vais vous donner la parole. Nous avons aujourd'hui le plaisir d'avoir avec nous Mme Lisa Wesson. Sally a étudié le génie civil et structurel au niveau du premier cycle et de la maîtrise à l'Université de Sheffield au Royaume-Uni. Elle est ensuite restée à Sheffield pour entreprendre un doctorat en génie de l'eau et qu'elle a obtenu en 2019. Le sujet de Sally est concentré sur la mécanique hydraulique transitoire, également connue sous le nom de coup de bélier, et a réalisé des expériences de laboratoire qui ont démontré l'influence de ces événements dynamiques à mobiliser des matériaux adhérents et aux parois de conduite d'eau potable. Ceux-ci pouvant être liés à la détérioration de la qualité de l'eau dans le réseau. Dans ses recherches postdoctorales, Sally a étudié la qualité de l'eau dans les réseaux de distribution d'eau potable. Elle a étudié l'approvisionnement intermittent en eau dans les pays en développement et dans le cadre de projets de recherche avec des partenaires au Népal, en Afrique du Sud et aux États-Unis. Ses recherches à l'Université Laval se concentrent sur une approche systémique de la qualité de l'eau et examinent comment différents facteurs comme la saisonnalité, l'âge de l'eau et les infrastructures peuvent interagir pour conduire à la dégradation de la qualité de l'eau. Le titre de la conférence de Sally aujourd'hui va être « Managing Water Quality in Drinking Water Distribution Systems ». Donc, Sally, can take the...
Hello, everyone. Apologies, this is in English. I'm learning French, but not enough to present in just yet. So I'm going to present managing water quality in drinking water distribution systems. If you have any questions, please put them in the chat, and I've recruited some translators for after the talk. So here we go. Ooh, there we go. So today I'm going to be talking about the complex distribution system. Since the Roman Empire, piped water supplies have been chosen as the most reliable means of delivering drinking water to households. By 2015, so only 6 years ago, the total number of people receiving drinking water through pipe supply was 4.7 billion, so 2/3 of the global population. The original role of drinking water distribution systems was quite simply to transport water from A to B. And historically, this was a very mechanical approach. It was the distribution systems were considered an inert vessel. If you've seen one pipe, you've seen them all. However, in the last about 200 years, there's been links established between health and water quality, particularly in drinking water. So we're now in this advent of safe drinking water needs, and utilities have a legal, economic, and moral obligation to meet water quality regulations. This shift in thinking about the distribution system as more than just a vessel has led to distribution systems being considered as dynamic, complex environmental systems where they are their own little world and they interact with their environment. And it's considered normal to think about the water as a changing substance as it's transmitted through the system, which is also constantly changing. So utilities now have to consider, how do we maintain water quality for customers? So what is water quality is a very good question to start with. The World Health Organization says that safe drinking water does not represent any significant risk to health over a lifetime of consumption, which is as vague as the World Health Organization is known for. The US Geological Survey says water quality can be thought of as a measure of the suitability of water for a particular use, in this case drinking, based on selected physical, chemical, and biological characteristics. And those three, biological, chemical, and physical, are considered the three pillars of water quality. However, the Encyclopedia of Physical Science and Technology goes a stage further and says drinking water requirements have been focused on elimination of pathogenic organisms, must be safe in terms of chemical constituents, and aesthetic water quality is also really important. So as you can see, there are multiple different things to consider. There isn't one unified definition of drinking water quality. Through my time researching drinking water quality, I've come up with 9 different themes, different factors about the distribution system that I believe make up water quality, either directly or indirectly. So what I'm going to do is I'm going to go through each 9, kind of describe them and what they entail, and we'll go from there. The first one is infrastructure. And this is the vessel. It's the physical system which the water is transported in. And that includes things like corrosion, pipe material, leaching, if there's any holes in the distribution system. And that's the physical characteristics that we talked about earlier. There's chemicals, and this is anything to do with chemical substances. So disinfection is the most common, looking at chlorine, disinfection by products, nitrification, metals, pH, anything to do with chemicals. And then there's microbiology, those 3 pillars that I talked about before. And this is anything to do with organic material in the distribution system. Biofilms, parasites, fungi, anything that is organic. There's also external contamination. This is anything entering the system that's not supposed to be there. It's not designed to be there. And this could be done on purpose if there's a terrace contamination, or it could be done accidentally. So if there's an environmental leak that just happens to be intruded into the system. There's hydraulic behavior, and this is anything to do with the physical behavior of the water as it moves through the system. So classically, that is velocity, pressure, stagnation, mixing, dynamic behavior, transients. There's all sorts of things that describe the water as it moves. There's water aesthetic. This is the perception of drinking water quality. So that's anything to do with discoloration, taste and odor, particles and sediment in the water. Technology is an emerging topic related to water quality, and this is anything to do with computing power, something the Romans definitely didn't have. We're looking at monitoring and monitoring capabilities, the development of new sensors, smart technology, the Internet of Things, machine learning techniques, anything to do with a digital chip. There's utility management, which relates to the operation, the stewardship of the utility with regard to the distribution system. And that might be pipe repairs, pipe replacement, flushing, designing the distribution system in a certain way, anything to do with the management of the system. And then the final factor is everything else, anything external to those 8 that I've talked about previously. External factors is the environment that the distribution system sits in. And there can be external sources such as temperature, source water changes. So if you're moving from groundwater to surface water, for example, any social aspects, all of a sudden the customers aren't happy for some reason. And these 9 factors all coexist and interact together to affect water quality. So I've made a little schematic to kind of represent what I'm talking about. Imagine our distribution system with the water treatment works. We have a mystery particle that's come out from the distribution system, come out of the water treatment works into the distribution system. It may interact with some old iron pipes that are corroded, and corrosion particles might enter the distribution system and join our mystery particle. At the ends of the networks, there could be some chlorine decay. And if the pipes are oversized, or if there is only one customer, we may get some stagnation. We can also get contamination from an external source, intentional or accidental. If we have suitable technology, we can monitor this and detect Any contamination or other undesired particles in the system are mystery particle, for example. The utility might decide to employ some flushing regimes to try and get rid of some of these particles. But let's say it's a really hot summer and we suddenly have increased temperatures. This may entice our biofilm to grow and perhaps trap our mystery particle. And the particles in the biofilm could react together to cause some pathogenic organisms to be released. Now, let's say we've got sudden shear stresses happening in the system because everyone's filling up their swimming pools, for example. The biofilm and the mystery particle are going to be mobilized. We get discoloration in our system, and all of a sudden, our customers are very unhappy with the way their water quality looks. All these factors, I've drawn them one by one to illustrate all the different things that can occur, but they may all be happening all at once, all in the same place, and everything interacts together. So as an overview of the project, we believe that utilities shouldn't focus on just one of these things. They shouldn't be examined in silos. All these factors coexist and interact together. Some random events can't be predicted and utilities have to be reactive. For example, if there's a huge storm, forest fires, the terrorists come out and contaminate all the drinking water. But for everyday proactive management, utilities should consider the big picture rather than all these individual factors in silo. So my project is a collaboration between Université Laval and Watershed Monitoring to develop a whole system decision support tool for water quality management in drinking water distribution systems to determine the causes, impacts, spatial temporal correlations, and mitigating factors for any risk to water quality in order to make proactive, informed decisions. And the idea for this tool is to integrate it with Watershed Monitoring's data storage and management software, Enki. But in order to develop this tool, we need to start off with the knowledge, the database of knowledge to extract all those causes, impacts, correlations, and mitigations to be able to build our tool with. And that's what I've been working on over the last 9 months now. I've been developing this database of knowledge. I've been searching for literature that's been published between 2000 and 2020. So it's the first 20 years of the 21st century. When I say it's a relevant source, I'm looking for something published in English so I can read it. It's got to be primarily about water quality between the water treatment works and the customer boundary. So for example, if a publication says, and water quality will be improved, it's not really good enough. It's got to be the primary focus of the publication or whatever the source is. It needs to be a typical system. So nothing atypical like rainwater harvesting, hospital settings, intermittent water supply, anything along those lines, and not epidemiological, so not related to health. As I said before, we all know that there's a link between health and drinking water quality, so I don't want to reinvent the wheel. My literature search took place in Scopus, and I found 13,000 possible sources. I've flicked through them all and assessed them if they are relevant according to these criteria, and my final list of relevant literature publications is 1,842 sources, which is quite an extensive list, but it just shows how big this field is in terms of research. With each of those sources, I've classified them by study type. And then this is how the research was performed. Was it a laboratory study, literature review, simulation, anything along those lines. I've also classified by study location, by country and region. And this is important to define study location as where the research was taking place, not where the authors were based, so not the university that was being represented. I also looked at study theme, and these are the 9 themes that I talked about earlier. And I also developed a list of potential topics. These are the smaller topics within the bigger themes. And each source was classified with 1 to 3 topics. So it might be disinfection byproducts and stagnation, perhaps fungi. Those are the 3 things that this paper is talking about. The classifications will ultimately be used to digest all this new knowledge and build a decision support system. But for now, I'm using the classifications to understand the global research landscape and how it's evolved over the first 20 years of the 21st century. And these are the diagrams, the figures that I've created that I'm going to present today. So the sources per year, as you can see from this graph, have increased. We only started with, in the early 2000s, about 40 relevant publications per year. We're now at 100. So it's massively increased. The field's got a lot bigger in terms of publications. 2/3 of the publications I'm looking at are journal papers. There's 31% are conference papers, which have waxed and waned over the years. As you can see, not many last year for obvious reasons. And the remaining 3% are other sources, and that includes things like books, technical reports, trade, magazine articles, anything along those lines. The study types have been broken down under the list that I mentioned earlier. 40% were numerical studies, so this is something to do with a simulation. And I've split those numerical studies into ones that were with a study location that was described. So some studies have just presented a theoretical network, or they've presented a network that can't be located. So I've called these just numerical case studies. And then I've looked at numerical with validation. So this is where the distribution system can be found. Over half of all the literature that I looked at included a real distribution system, a distribution that had a known location that could be given for context, whether it was a numerical study or a field work study. 17% were laboratory, and the remaining publications were either literature review, framework and methodology, or regulations and policy. Numerical with validation and operational networks were the ones that grew the most in the last 20 years. So this is a really big plot. I'm just going to explain what the figure shows to begin with before I go into any of the information. On the left is the relative abundance of the locations, the regional locations of the literature and how they changed over the 20 years. The numbers at the top, I don't know if you can see my mouse, but the numbers at the top are the total publications per year. And this pie chart on the right is the summary. It's the total over the 20 years amalgamated together. So there's a few things that jump out here. As you can see from the pie chart on the right, a quarter of all literature didn't have an associated location. So for example, if it was a generic literature review, it didn't have a location, so it was put in the not applicable category. However, over half of all literature had either North America or Europe as its case study location, which is not very surprising, I don't think. In total, 57 countries were represented. As I say, North America and Europe were most dominant. However, Asia, the Middle East, South America and Africa increased over the period. So if I can draw a line here, can you see that the other nations that are not North America and Europe are increasing over time? So North America and Europe are still publishing quite significantly, but the market is becoming more diverse. We are seeing more studies represented around the world. The first time all regions were included in my database was 2009, and then 7 out of the following 10 years were fully diverse, as it were. Okay, the next plot is study themes. So it's the same type of plot with relative abundance over the 20 years on the left, and then a summary of the 20 years as a pie chart on the right. Not surprisingly, the biggest themes that were published in the research were related to technology, chemicals, and microbiology. However, you can see that they do change over time, and the field is quite diverse. There's quite a lot of representation of all the different topics. So it's not that one topic dominates, it's a fair selection. So going into the topics a bit further, these are all the smaller research focuses that I mentioned. The most popular ones were anything to do with simulations, biofilm, chlorine, intrusion, and monitoring. The least popular were backflow, pipe maintenance, pumps, parasites, and fungi. However, I noticed when I was putting the topics together for each publication that some were found together more often than others. So for example, simulations in chlorine were often assigned together, but pH and pipe material were never assigned to the same publication. This figure on the right shows the links between the different topics that were assigned for all the publications. The colors don't indicate anything in particular, that's just for visual aid, but the thickness of the line shows how popular they are. So you can see that simulations and intrusion, simulations biofilm, simulations and monitoring, simulations of chlorine, anything to do with simulations was quite common. However, some of the others, such as pipe maintenance, was not that popular as a topic. The top 10 popular countries, I saw that over half of all literature sources referred to just 10 countries. So 57 were included, but 10 dominated, and these are our top 10. The USA was the largest, with a 21.6% total share of literature, but that did decrease over time. China rapidly increased over the last 5-6 years to reach ranking number 2, as it were. And what we can see here is that each country has its own research identity, and this can be a product of research goals of particular researchers, or if there's a strategic priority for the university or country, and other such factors such as funding. I just want to highlight that in Canada, the most popular topic is disinfection byproducts, and I think we all know on this call who is to blame. Discoloration in the UK is the most popular. However, biofilm is most popular in the Netherlands and France. So there's different identities going on with these countries in terms of research and water quality. The next steps of my project are to determine which of all these literature sources are useful to the decision support system. So I might create some matrices or some kind of way of ranking the publications to see how they are relevant. And hopefully this will give us a small database of knowledge that we can use to extract all the causes, impacts, correlations, and mitigating factors for water quality risks. And then the stage after that is to use machine learning to build the decision support tool. The end. Thank you for listening.
Thank you for this nice presentation. We have some intervent and some text in I don't know the word in the chat. Excuse me. From Isabelle Sawyer is more commentary. Actually, in Quebec, we historically mobilized successfully to defend that water not become a product for companies to make a profit with beings that drink or use water do not become consumers. Indeed, a movement, political and in law, in a motion to recognize the rights of nature to courses of water as a St. Lawrence to ensure water quality for all on land and sea and for generations. People drinking water are not consumers. It's the moral statement. And we have a first question from Julie Gauthier.
Can I just
you can add, yeah, excuse me.
The reason for using consumers rather than customers, typically customers is a more common phrase for people who are billed for drinking water. However, there are some parts of the world where people need access to water, so they tend to add their own connections without having billed connections, which is where consumers is more of a generic term that I've come across. I absolutely understand what you're saying about people's rights. However, just that's the terminology that I've always used, is rather than customers have consumers to incorporate more people who use drinking water.
If I can add, the fact of using consumers, I understand, is even in Quebec we can use that. Sometimes we use citizens. Drinking water is produced by municipalities, even if it's not metered to be paid in function of the volume water is produced by the municipalities with infrastructure. I'm talking about drinking water. So the public, the citizens, are consumers as well in terms of asking to the municipality to comply with all regulations to receive the needed amount of water at every moment, at every location of good quality. So in these terms, we are all consumers, and municipalities, they have the responsibility of providing an adequate quantity and a water without a risk or with a minimum risk. In these terms, we can use citizens, but we are also consumers.
We also use users. Users is
that's right.
Another term. Yeah. From Julie Gauthier, we have a question. Have you found any studies that make the link between the type of geology in which the groundwater circulates, for example, type of rocks, and the quality of the water in the aqueduct network or networks? Groundwater often ends up supplying surface water.
So this isn't something that I've particularly looked into. My research is always focused on the distribution system post water treatment works. So my input tends to start believing that the water treatment works as intended. I'm sure there will be some studies out there looking at the relationships. I'm sure Manuel and everyone else can give more information, but that's not something that I'm involved in.
Yeah, however, maybe, yeah, you're right about this link, because I think that the question is about the link between groundwater and surface water at the source. However, in relation with the groundwater quality or the soil quality, there are, I think, some studies that show that intrusion of water from the soil, from groundwater, eventually contaminated, in some circumstances can produce distribution system water quality contamination. I don't know, Sally, if you have identified papers on this issue, on the fact that soil contaminants in groundwater can affect the water quality within the pipes.
There are some papers in my database that are looking at source water quality and how it impacts the distribution system. I can't currently comment on what they're saying. I need to read them in a lot more detail. I wouldn't have come across them normally, but it's my intention to understand. So maybe in a few months, I'll be able to answer that question.
We don't have any more question. Do we have some people have, don't be shy. You can ask a question in the, oh, we have a thank you here. And okay, you spoke about aesthetics in water, and it's my field of interest. I'm very interested by this thing. Sometimes we have a link between aesthetic consideration like conductivity, sodium, chloride, anything like that, or color, and sometimes they can lead to a problem in the quality of water. For example, conductivity can leach the pipes, the metal in the pipes, and conduct in the metal contamination in water, drinking water. Do you read some articles on this or some paper on this?
So my understanding for water aesthetics in general is if you've got to the point where people are noticing water quality,
okay,
water quality seriously gone wrong.
Okay.
So for example, if there's a discoloration of about 4 NTU, which is when people start to see the water's discolored, then most likely you've got all sorts of microbiology and sediments in there that you don't want anyway. But I know in the UK, it's what utilities tend to be fined on. So if a customer calls up and says, my water doesn't look right, utilities can be fined something like £3,000, which is maybe $5,500, something like that, for every customer that complains. So that's why water quality, in particular discoloration, is such a big issue in the UK. We have very old pipes that give off brown water and black water, which is what people pick up on and complain a lot.
With a lot of iron, maybe, or manganese, or anything like that.
Yes, iron and manganese are the worst.
Yeah, yeah. And actually, I have a question. Have you observed specific themes according to geographical locations?
Yes. So these are the top 10 countries. If I just go back a little bit, if I can I go back? Here we go. So I have noticed that where you are gives a kind of interpretation of the research you're most likely going to be looking at. So for example, in the Netherlands, they don't chlorinate their water. So they tend to be quite driven to look at biofilm because it's the microbiology that can be, it can grow quite quickly if there isn't the disinfectant in the system. In America, intrusions and simulations are the most common topics by a long way. This is most likely in a reaction to the 9/11 events. I did a quick analysis of countries that, publications that refer to some kind of intentional language of contamination, and quite a lot refer to the events of 9/11, and that's most popular in the US. So I don't know if you remember the slide, I'll just find it. The slide where we looked at sources per year. Between kind of 2005, 2006, 2007, this bump in the middle is driven by papers looking at the topics of intrusion and simulating intrusions and contaminations, and they coincide with publications in America. So there's definitely a link there between causes of publications and themes and locations.
Sonia Bemel said, thank you very much for your presentation. Based on your own opinion or knowledge, excuse me, it's moving actually. Okay, and where should be the main focus on future research relatively to changes in water quality in the distribution system?
My interpretation of future challenges are going to be dominated by climate change and increased temperature in the distribution system. If you have increased temperature, biofilms are more likely to grow, and that can cause pathogens to grow. And that's the biggest concern for water quality, is something that's going to upset people on a health basis rather than the water just looks a bit funny. However, I was surprised, if I look on the studied themes, that wasn't as popular as I thought it was going to be. I thought it was going to be increasing. In the future, there might be challenges around chemicals being available. So for example, I think phosphorus used for disinfectant, there's a limited amount of phosphorus, and it's becoming more expensive for utilities to use, I believe, if I'm right in saying that. So there might be a balance between external environmental impacts on the distribution system, such as temperature, with how can we disinfect the water to be able to balance the biofilm that grows as a consequence of that temperature. That would be my gut feeling, but I currently can't back it up with any numbers. But I think, yes, the balance between discoloration and temperature, I think, is going to be the biggest issue.
Andres Ardila Jimenez, thank you very much for your presentation. Do you think that the lack of articles produced in tropical countries can influence the understanding and optimization of water quality in the distribution network in those countries?
Yes, I'm going to link this as well with the next question, which is about leaving out atypical systems, because I found that the two relate together. So in places, in the more tropical countries, so for example, Southeast Asia, Africa, South America, they tend to have intermittent supply more so than North America and Europe. So I've chosen to leave out intermittent systems because the research is emerging and there's still a lot of questions to be known. So I do think that is a failure of this study to only look at what I've called typical systems, because it does bias against some of those countries. So that is something to address in the future. There are huge water quality implications for intermittent supply, for example. Decentralized systems, which are more popular in tropical countries, are also something to consider as a different type of distribution system. So by including those atypical, as I'm labeling it here just for ease, but I don't mean any offense by that, is just to narrow down the scope a little bit. However, I do think intermittent systems as another alternative to continuously driven systems is something that we can massively learn from. So I know there's places in the UK and southern Europe that are struggling with temperatures and have looked at intermittent systems as opposed to continuous systems. So I do think there's a lot for the typical wet and dry, the wet countries, to learn from the tropical countries in terms of intermittent supply and other alternatives. So that is a failing, to answer David's question, of this study, but it's just to focus a little bit. But that's something I will discuss in future work. Hope that answers your questions.
David, I don't know his familiar name. Why did you decide to leave out atypical networks? Wouldn't it useful to include those case studies as outliers or extreme events, especially considering that there are a lot of DWDS that are atypical?
So this is what I was talking about with the intermittent systems. Almost half of all distribution systems are operated intermittently. So there's a huge argument, why am I ignoring half the distribution systems? And I understand that and I appreciate that. It's just a way of narrowing down the scope of this project. That's the only reason.
Okay, thank you. From Tricia Brett, thank you for your presentation. Through your research, could you comment on where water utilities could be focusing budgets to improve drinking water quality in Canada?
Oh, that's a big question. I don't think I have the expertise to be able to answer that question. At the minute, I do think with this project, we are trying to push for an integrated understanding. So I would argue, and I hope Sonia would be able to give a bit more substance to what I'm saying. I would argue that management and being able to understand how all these factors interplay is a good use of budget. And I would say that because that's what's funding my work. But I do think that if you are trying to use the budget to put out one fire after another, you're not really getting to the heart of the problem. So you might be spending a lot of your budget trying to understand discoloration, but actually if you use the budget to understand biofilm behavior which influences discoloration, you can tackle the problem more upstream and get to the heart of what's actually causing all the fires that you're putting out, would be my argument. Sonia, do you have any thoughts?
Should I open yes. her camera?
Yes, well, it is truly a big question, and I think it can only be answered for each utility in itself, and that also according to the quality and challenges of its source waters. and the specificities of every system. So I think the baseline to take any decisions would be to have the entire information on the water cycle from the source to the tap, as well as the information on the problems or challenges within the watershed, geological realities, land use, as well as meteorological and climate conditions, and then also, of course, how the water is being treated and distributed. So I think the entire, the picture must be as holistically as possible in order to be able to take those decisions. And I would like Francois actually to let me know whether I, if he thinks that I gave the right elements also, just to confirm, because I'm more the source and less than the distribution.
Well, we have a lack of investment in distribution system in the Canada, and we have some problem with pipes in some places. Okay, I think it's.
If I can complete, Francois,
yeah,
I agree with these answers, and in fact, it's depending on how the question is asked. If you ask us what the government have to do to improve water quality, drinking water quality, is different that asking what the municipality or a municipality have to favor in terms of water quality, because in a municipality scale, it depends on the specific issues, as Sonia mentioned, of the municipality, but the government level, probably the more important thing is trying to provide safe water to some communities that don't have.
Yeah.
That was my comment.
Especially for First Nation communities in Canada, they have some problem with the water quality. Okay, I think it's done for a question. Okay, we will finish. I thank you for this presentation, and I hope you excuse me my big accent in English. And for this conference, I will continue in French. OK, en conclusion, donc, on vous remercie à tous et à toutes d'avoir assisté nombreux et nombreuses à ce programme de conférence de l'automne 2021, de la chaire de recherche en eau potable, mais aussi du CRAD. Il y avait 2 conférences qui étaient présentées en collaboration avec le CRAD. Vous recevrez dans les prochaines semaines, je travaille là-dessus avec Manuel, la programmation pour l'hiver 2022. Donc, on travaille là-dessus. Et puis, je vous souhaite de joyeuses fêtes. Peut-être que Manuel voudrait prendre la parole. Je vois ton écran grandir comme ça.
Ah, OK, je ne savais pas. En fait, non. Merci à tout le monde, comme François dit. On va continuer dans cette lancée de série de conférences sur l'eau. Et merci à François, surtout, qui a organisé depuis 1 an et demi ces conférences qui sont toutes un succès. Et joyeux temps de fête à tout le monde.
Reposez-vous bien et revenez-nous en santé au mois de janvier. Au revoir à tout le monde. Bye. Thanks again, Sally.
Thank you. Bye.
Bye.